ब्रेक करनी है या लगे रहें बस 8:30 तक कर देते हैं 8:20-25 तक, उसके बाद फिर आज़ाद ब्रेक तो कर दी।
हाँ सही है सही है
ठीक है जी। So that's infinitesimal generator. So shall I put this conclusion in the form of a theorem? Okay, so let me make a neat theorem out of it. So here's the theorem. So the generator of Ito process, that generic Ito process that we wrote, Ito process is this A, that is 1/2 of Ij of sigma transpose Ij partial 2f by partial Fn xi xj plus sum dk and partial by partial k. ठीक है? So this is really the infinitesimal generator. ठीक है? ये जो sigma matrix है, sometimes you call it a dispersion. Okay? And this product sigma t transpose, this is really sometimes called the diffusion. ठीक है? So we call it diffusion. ठीक है? 2.6 and 9.5. Okay. If you take this equation, then this is your infinitesimal generator. ठीक है? So एक आखिरी आइडेंटिटी that we can write इसी इक्वेशन को लिखूं तो क्या होगी? So the conditional expectation of f of x t is equal to f of x plus the conditional expectation of the generator of what do you call it? The Ito process actually. ठीक है? Generator of Ito process.
So under what conditions in general?
जनरल है ना, इस आइडेंटिटी को देखो ना, सॉरी इस लिमिट हटा के, लिमिट को बाद में ले रहे हैं, so I'm saying that just keep it as it is. ये ऊपर वाली इस ऊपर वाली इक्वेशन पे एक्सपेक्टेशन अप्लाई करो. So I'm not talking in the sense of the limits actually.
सही है.
So forget about limits. ये इक्वेशन ले लें और एक्सपेक्टेशंस ले लें. So you have the expectation of this plus f of x times expectation of this infinitesimal generator. चाहे आप कितना भी applied mathematics कर दें, so no matter what level of applied mathematics you do, you always have to justify your equations in mathematics actually. So you always need such kind of analysis. इसके अलावा हवाई बातें हो सकती हैं, but not something that you can do as interesting actually. ठीक है? Okay, the next is on Dynkin's formula. So what does Dynkin's formula is doing? Shall I get into that? So the Dynkin's formula, यहाँ भी f of x of t है. So you have this equation. So what is Dynkin's formula? You may see its proof from the book. Okay, I'm not getting into it. But the Dynkin's formula is that this same equation of the conditional expectation also holds for a measurable stopping time actually. So in other words, if you replace t by a stopping time, this would also work. So expectation of f of stopped process at tau is equal to f of x plus expectation, conditional expectation of infinitesimal generator evaluated at fx at tau. Okay, so that's really the Dynkin's formula. Okay, the proof is in the book. It just proves two lemmas and okay. Okay. Same equation, but with the stopping time. So what is the relation of this with what you call the theory of PDEs actually? Okay, all this stuff. Okay. And why I was saying that the infinitesimal generator is a nice tool that allow you also, to compute, for example, the solution of a given, for example, kind of a PDE, good PDE. So here's the thing. So the Kolmogorov backward equation. Kolmogorov backward equation. Simple. It's a simple calculus. Simple calculus. So let's take an f that is, twice differentiable, and it has this compact support. Okay? So it has this compact support. By compact support means that it vanishes outside the boundaries actually. Okay? We know what was the meaning of support of a function, remember? So the support of f is the collection of those points for which f of x is not 0 actually, and you take the closure of it. Okay, it's a closure of it. So in other words, support of f is the collection of all those points for which function is 0, not 0. And if you take anything outside of the support, the function will be 0. Okay? So it has this support is compact. Okay, so maybe we will not use too much of it. I'm just recalling this actually. Okay? And you can quickly have a look on it. And let's call this expectation, this conditional expectation, and give it a name Vtx. Okay? So I'm calling this, expectation a function v that depends on t and x. V of 0x would be what? So it simply would be f of x. ठीक है? इसे मैं इंटीग्रल शक्ल में लिख सकता हूँ. Can I write this as integral in the integral form? जो लास्ट इक्वेशन है ये इंटीग्रल की शक्ल में है. अच्छा, हमने जो है जो गड़बड़ की है वो ये है कि यहाँ इंटीग्रल होना चाहिए भैया. Can you see why? Can you see why? Yes. So what was my ft? Remember ft? So it was f of x plus integral of this entire guy.
Yes.
And this entire guy is really what do you call
सही है.
the af of xt actually. ठीक है? And then you take the ex of it plus what dw वाली term भी होगी, but when you're gonna e of this, so you're gonna have the ex of this term will go and you're gonna remain with this entire.
Yes, sir.
Right?
Yes.
देखो ना. So ft was what? तो समझ आ रही है बात?
जी.
क्या समझ आ रही है? That ft was f of x plus an deterministic integral plus an stochastic integral. ठीक है? And then you take the ex of it. So it's going to be f of x plus ex. But the ex is going to be this plus this, but this will go away. ठीक है? और जो यहाँ बचेगा, what was this actually? So this was really a of fx actually. a fx ये था. ठीक है? So इसमें थोड़ी सी आप जो है इसमें भी correction कर दें that you're gonna get I think 0 to tau s and ds. इसमें भी correction होगी. ठीक है? उसमें correction होगी तो फिर इसमें भी correction होनी चाहिए. Yes. ठीक है? Okay. So with this now, we should say that यहाँ पर है जी हाँ ठीक है. So v of t is this, and then using this identity, I'm gonna have v t x. ठीक है? f of x plus
expectation of
conditional expectation of integral from 0 to t a f of
s
x s and ds actually. ठीक है?
सही है.
And then I can do what? I can say that this is an integral and this is an integral, and
This is derivative a.
ये a का derivative है.
ये a और ये t है.
So first of all, I can exchange these two integrals like apply Fubini. So we can have 0 to t, ठीक है? ex of a f x s ds, ठीक है? And then f of x plus 0 to t, even I can switch this a and x. So it's differentiation and integral sign. So I can say it's a of e of fx of x, which is vs
x
x and
ds.
ठीक है? And then differentiate it with respect to time. So we're going to differentiate it with respect to time. What are you going to get? So if you can differentiate it with respect to time, we'll have partial v by partial t. This would be 0 plus is going to get rid of this integral actually, and you will have a v and simply a v. Okay, and this is v0 x is equal to f of x actually. So what does this show? What does this show? This shows that this conditional expectation is a solution to a problem in which, so it's like a PDE, okay, bracket PDE with the operator a, and this operator a is the infinitesimal operator. ठीक है? So it's a solution of this.
सर प्रॉब्लम के corresponding हम वो ये ऑपरेटर फाइंड कर सकते हैं, ये जनरेट
This is what the really thing is, that if you want to solve this kind of a problem with some operator, you can say that the solution would exist if and only if this operator A generates really an Ito process actually. Or for example, function analytically we say that it generates a semigroup, C0 semigroup. Okay, so this is what essentially we are saying.
But here also C0 will semigroup.
No, it is C0 semigroup. No. So C0 का मतलब है like it's a C2 class function with a compact support actually. So it's not
zero is compact support.
Compact support. Assumption on conclusion ये है. Okay. So imagine I want to solve, for example, this PDE, partial V by partial V equal to del V, and Vx0 is equal to some function f of x. Okay. Now here what I have is a Laplace operator.
Okay.
So, and I want to know that does solution of this function exist, or does solution of this problem exist. This result is telling you that if this operator, the Laplace operator, which is often called a diffusion operator, that's why you call it a diffusion actually, generates an Ito process. Okay. If this operator is a generator of an Ito process, then yes, you can have a solution, a unique solution of this problem actually. So if it generates an Ito process actually. So here I have this Laplace operator, but you can have any other operator. You can take a Schrödinger operator actually, and this becomes a what you call Schrödinger wave equation. Okay, and then you say, does the solution of Schrödinger wave equation exist? So then I'm going to say that. So it's like so the answer is going to come from the fact that does the Schrödinger operator generates an Ito process? So if it generates an Ito process, yes, solution exists. And what is that solution? The solution is simply this conditional expectation actually.
What f would be used there?
So the f is this initial condition. F is your initial condition. If you haven't given an initial condition, just compute the conditional expectation of initial condition.
With that process.
For that process, you get the solution. Yeah. No, but as I'm saying that, like such results are even, available when A is more general. So A is specific here. I can see your point. A is specific here. And you can see a lot of operators would be very particular case of this. For example, what would be Laplace operator actually? So take all these to be 1s and take B's to be 0 actually. And that's a Laplace operator. So there will be a lot of complicated, for example, even I think that the Navier-Stokes equation can be got from it actually, which is the pivotal equation in fluid mechanics actually. Wave equation certainly can be obtained from it actually. So you're not talking about one problem but a class of problem actually, and that's what makes it. Okay? So what is the key thing that you are having here? That the generator, so if you have a generator of an Ito process, okay, so if you have an Ito process and you have a generator of it, okay, then you can have the problems of such kind of a solution. Or other way around, you can say that if you have a problem, such kind of a Kashi problem, which depends on some generator, so you just say that does this generator generates some Ito process actually or not. Okay? So this can be generalized even to semigroups actually, that if it generates a semigroup, you're going to have a more complicated kind of equation. Is it making sense? Okay. Alright. Her Ito process, so in this we have a Ito process has a generator actually of this form. Okay. So you can write a differential equation. So just write a one-dimensional differential equation of it. And now you can, using this formula, you can say that what is the generator of this, what is it called, process actually.
But here we have other case, like we have the generator here, and then we have to find the process to find the solution.
Yeah. So this shows that how this PDE is really linked with this theory of what we call a stochastic process. Okay, so it gives the beautiful links, how things are related with each other.
सर मुझे बस ये समझ नहीं आ रहा कि हमने प्रूव जो किया है वो इसके लिए किया है, लाइक हमारे पास स्टोकेस्टिक प्रोसेस है, उससे हम जनरेटर बना रहे हैं,
ठीक है,
फिर उसके लिए ये ट्रू है,
उसके लिए,
लेकिन हम अगर हमारे पास एक जनरेटर है,
so in other words that मैं समझ रहा हूँ, we are talking about the converse actually. We are talking about the converse, ठीक है. So you can also have a converse of it as well. That यदि आप एक PDE उठाएं and you have an operator for it, सिर्फ इतना देखें, does it generates ito process. अगर वो generate करता है ito process तो ये solution है इसका. So just compute this expectation and you have a solution of it. That's it.
Initial condition.
ठीक है.
Condition.
So both are linked actually. ठीक है.
और सर वो ईटो प्रोसेस जनरेट कर रहा है, वो कैसे हमें पता चलेगा?
क्या मतलब?
जनरेटर
ईटो प्रोसेस की मदद से ही तो हमने कैलकुलेट किया ना इन्फिनिट एस.
नहीं अगर ऑपरेटर हो मतलब जनरेटर हो तो
हाँ, तो हम ये कहेंगे कि जी ओके, लेट्स टेक द ईटो प्रोसेस एंड कंप्यूट इट्स जनरेटर एंड सी दैट वेदर यू गेट दैट generator or not. हाँ, I can see your trouble. How can you show that it generates? Then you have this beautiful theorem, it's called the Hilly-Yoshida theorem actually. ठीक है? Hilly-Yoshida. So the Hilly-Yoshida, एक Hilly-Yoshida theorem है और एक Lumer-Phillips है. So the Lumer-Phillips theorem and Hilly-Yoshida theorems are the two theorems which tells you that what you have to do is that you have to study the resolvent of this operator. So whatever operator is given to you in a problem, if you have been given an operator, so you need to study the resolvent of this operator actually. So R lambda A. So the R lambda A is really A minus lambda I inverse actually. Okay, so you need to study the resolvent of it, and what actually you need to show is that if you compute the norm of this resolvent, is this less than or equal to some 1 over lambda? If this is true,
then it generates
a system. Okay. So it's like eigenvalue. So it's like eigenvalue problem. That's what I'm saying. So when Shinal was presenting this, मैंने कहा यार ये तो वही चीजें कर रही है.
Sir, assumption तो हम इसमें देखें.
Obviously there are going to be assumptions. So I'm just giving you really a bigger picture actually, that so you have theorems that give you sufficient condition to say that A is going to generate a ito process or a semi-group in general actually. It's more generalization of it. ठीक है? खत्म करूँ?
Only using the
there's a lot of waving of hand actually, but you know,
bigger
picture तो पता चल रहा है how things are related. ठीक है?
आप एक ईटो प्रोसेस लेंगे, उसके लिए ये सारा ट्रू होगा, मतलब ये
Yes.
बिगर क्लास ही है.
You mean in class? I mean, think about it. As I'm saying that this operator can be crazily anything.
सर तो इसका मतलब अगर
ढेर सारी तकरीबन जितनी भी equations आपके पास है. So even wave equation can be written in this form actually. So you might have seen, okay, the wave equation is the second order time derivate and second order space derivate actually. But what you can do, you can write the wave equation in matrix form. It would be of this form actually, where A is a matrix. Okay. And then, you know, through Hilly-Yoshida you can say that, you know, it satisfies, if the resolvent satisfies some property, so solution exists. ठीक है? भाई आखिरी 5 मिनट है. सिर्फ एक चीज करते हैं कि what would be the expected time that the Brownian motion is sitting inside a ball actually of a radius r. ठीक है? Will be the last thing. So let's consider a ball of the radius r. Let's consider a ball of radius r, and the radius is really at the origin. Okay, and imagine that from this origin, kind of there is a particle or an object which is starting moving randomly, and so it just moves randomly, and it exits this radius actually. And what basically I'm interested in, and this, for example, process is, let's assume that it's Brownian motion. Question: what would be the expected time that Brownian motion will leave this radius actually? This ball. So that's what is the one of the problems. So there are many things that you can answer through these really silly formula. ठीक है? Okay. So let me define in the stopping time, tau. So tau is the first instant t bigger than or equal to 0 such that
it leaves
the process xt
Is no longer.
Gets bigger than or equal to r, it leaves the r actually. And what is xt? So xt is a plus wt, so it's a shifted Brownian motion actually, where a is a vector a1, a2, an, and w of t is w1 of t up to wn of t actually. ठीक है? So I'm saying that what is the problem? I mean, you can take a equal to 0 and you get the probability of, as you take a equal to 0, you're going to have the stopping time when the Brownian motion leaves this radius actually. So it's really the shifted Brownian motion. ठीक है? So I'm going to use Dynkin formula. So keep Dynkin formula in front of you. And the function that I am choosing is the magnitude of x actually. Okay?